We are recording. We're in now section 12.7. We're talking about another application of double integrals, and this one deals with surface area. Now, let me ask you, are we able to find, for instance, the surface area of a box? So is it possible to find the surface area of a box without too much trouble? How would we do it? Okay, that's right, Norina. We would find the area of each side and add up those areas. So the surface area of a box is no big deal. Is there a formula for the surface area of a sphere? Has anybody seen a formula for the surface area, for instance, of a sphere, or maybe a cone, or a cylinder? Has anybody seen surface area formulas for those type of, maybe in high school? All right, Simon recalls that. Yeah, so some of our very common solids, there are actual formulas for the surface areas, and those formulas are derived. They can be derived using the approach we're talking about here in section 12.6. But what we want to do now is we know we can find surface areas of very standard solids. But what if, for instance, we wanted to find the surface area of a bowl? Okay, the surface area for a bowl. Okay, that would be of interest, but yet we don't necessarily know a formula for the surface area of a bowl, but we can come up with one. So let me show you, let me sort of guide you a little bit through this section 12.6 on surface area to show you how this works. So first of all, in figure 1, we have a surface. And we're looking at a point on the surface, P sub 0. Now, through point P sub 0, there are two space curves. You can see them in the picture, space curve C1 and space curve C2. If we go back a little bit here, recall from section 10.5 that a parametric surface S is defined by a vector value function of two parameters. So, for instance, there are like the vector value function of two parameters. With that, we can trace out a cylinder. We can trace out, a cone. There's a variety of, we can describe surfaces by tracing them with a pen. And as we trace the surface with the pen, it reveals the surface. Well, how does the pen move? It moves according to a vector function formula of two variables, u and v, two parameters. And as the parameters u and v vary, that moves the vector and scratches out the surface. So what they have here in this figure below, in figure 1, they have the surface below, but then at the top part of figure 1, what are they doing? You have a domain that contains all the parameter values of u and v. But if you hold one of the parameters fixed and let the other parameter vary, you're going to then trace out two space curves, and those are the space curves that you see on the surface. Now, for each of those space curves at a point P sub 0, there are tangent vectors. The tangent vectors are tangent to the space curves at the point P sub 0. But also remember, those two tangent vectors, if we limit how far they go, they can trace out basically, well, I want to say this the right way. They can trace out a parallelogram to a point on the surface. So the tangent vectors, okay, here is, and you've seen this a little bit in your homework, and even been, you've seen this a little bit in your homework. Here is the vector function. It's the tangent vector that where you hold the, I'm going to say this the right way. All right, I want to say it the right way. Okay, so let me go up here a little bit. Hold on. No. Up a little bit. Let me take off this highlight. So this vector function of two parameters, if you hold the u variable constant and differentiate that vector function then with respect to v, that's going to get you r sub v. If you hold the variable v constant and differentiate then that vector function with respect to u, which is now the only variable, then you have the tangent vector r sub u. The figure below here, in figure 1, the surface there are those vectors r sub u and r sub v. Those are the tangent vectors to a point on the surface. And the point, but those tangent vectors, I want to say this the right way, are tangent vectors where you have specific values for the parameters u and v, u sub 0 and v sub 0, because you have to have specific values because you're at a point on the surface. And the vector function, the vector function traces out the surface as you vary u and v. Okay, I'm back. How long was the audio off? Was it off long? I hope it wasn't. Was it only off for a moment? 45 seconds. All right. Let me go back. Thank you. Let me go back. Hold on here. I'll repeat what I said. One moment. Okay, so this vector function of u and v, as u and v varies, as u and v take on different values, the vector function scratches out a surface in space. Now, when u and v are particular values, you are at a point on the surface then. Okay, it's like holding a pencil and touching a point on the surface. So that's what you see here in figure 1. That's what you see. You see a point on the surface for a particular value of u, which is u sub 0, and a particular value of v, which is v sub 0. Now you have these tangent vectors with respect to r sub u. You have r sub u and r sub v. Those are tangent vectors to the point p sub 0 on the surface. Notice that those tangent vectors are tangents to two space curves as well on the surface, and those space curves correspond to holding one of the parameters constant, and that's what you see there up on region D. Okay, so one line segment is when you on region D is letting u equal a constant. That's the vertical line segment, and that would then the vector function when you hold the u parameter constant would trace out one of those space curves. It would trace out the space curve that goes with hold on here, that goes with C1, and then the second space curve C2 corresponds to holding the parameter v constant, and that's that horizontal line segment on region D. So why is this important to us? Well, first of all, let's recognize that these two vector functions, r sub u and r sub v, on that surface are vector functions where you have substituted in a value for u and a value for v, right? Because they are at a point, and a point on the space curve corresponds to a specific value for u and a specific value for v. So given that, the tangent vector r sub v is defined equals this, right? And you are again you're holding the u variable constant, evaluating those components with respect to v, and then putting in the value for the v variable, v sub 0. The r sub u, the other tangent vector, you're holding the variable v constant. It equals v sub 0. You're differentiating the components all with respect to u, and then you're putting in u sub 0, because u sub 0 and v sub 0 correspond to that point p sub 0 on the surface. And there are your two tangent vectors. Now, how does this relate to surface area? Well, first recognize for any point on the surface, we can find two tangent vectors. And, you know, what we can do with the two tangent vectors is we can actually form a parallelogram with the two tangent vectors. So you see there in figure 3a, oh, well, what's that s sub ij? Well, let me show you. So in figure 2, okay, you have a surface. Now, one moment, take a look at it. Take a look at it. Yeah, you have a surface. There's that piece, the point on the surface, p sub ij, and then a patch, s sub ij. So you can think of the surface as like a quilt with a bunch of different patches. And to find the surface area of the quilt, we need to find the surface area of each patch. Well, each patch, okay, can be approximated. You can approximate the surface area of the patch with the parallelogram that's composed of those two tangent vectors, r sub u and r sub v, at the patch, coming out from the point at the corner of the patch, of that patch. So each patch on the quilt corresponds to a different point. Every point has two particular tangent vectors that emanate from it. But you'll notice here in figure 3a that if we were to find the area of the parallelogram formed by those two purple tangent vectors, we'd be missing some area of the patch. You know, the area of the parallelogram might not approximate the patch surface too well because this patch surface isn't completely flat, right? And there you can even see a gap there in figure 3A. You can see a gap. So it's an approximation. But what you can do to make the approximation a little better is you can actually take those tangent vectors and multiply them by little deltas. So delta u multiplies the tangent vector with respect to the r sub u vector. And so delta u times the tangent vector r sub u. Okay, that'll make the tangent vector shorter. So that, I mean, what I'm trying to say is, if you think about this quilt and you take more and more patches of the quilt, the patches of the quilt start looking flat and they start approximating parallelograms. So the idea is break your quilt up into a bunch of these little patches and approximate each of the area of each of those patches with a parallelogram. But how can we break up the quilt into a lot of little patches? Well, we can pick points, a lot of points on the quilt, but for every point, adjust the tangent vectors r sub u and r sub v by multiplying by delta u and delta v to make the tangent vector short. And so you have a very small parallelogram that approximates the patch where that parallelogram is. I'm going to say this right. You'll have a very small parallelogram that has these tangent vectors r sub u, r sub v that are adjusted in length by multiplying by the little delta u and delta v values. And those vectors themselves will form a very small parallelogram that will approximate the patch there very nicely, the surface area of the patch. Okay, so again, you're finding the surface area of a patch with the area of a parallelogram, but you have to make the tangent vector short so that the area of the parallelogram nicely approximates the surface area of the patch there. All patches, when you're focused on a very small portion, a very small patch, all patches will look flat, right? All patches will really look flat and will be approximated. The surface areas of the patches will be approximated by the area of the parallelogram. So what you have to do here is, okay, what would the area of the parallelogram be? Well, you remember that back when you learned about the cross product, you learned that the cross product, I want to say this the right way, the length of the cross product of two vectors equals the area of the parallelogram formed by those two vectors. Right? How many recall that? That was, we learned that back in section, I want to say this, section 9.4. Okay, it's something you learn. If you go back to section 9.4, we saw that. So in this picture here, we want to find the area of that parallelogram formed by sides delta u times r sub u and delta v times r sub v. The area of that parallelogram is going to equal the length of the cross product of those two vectors. But delta u and delta v are scalars, right? They're scalars, they're multiples of those vectors, and we can bring the multiples out. And so now the area of this parallelogram, of a small parallelogram, is just equal to the cross product of the tangent vectors, or I should say the length of the cross product of the tangent vectors, times delta u times delta v. That's the area of one parallelogram. Okay, and if you wanted to approximate the area of the entire quilt, just then add up all the areas of the parallelograms, and that gets you this double Riemann sum. Naturally, I think you know what's coming. If you let m and n go to infinity, that means you're letting the patches, you're taking more and more patches. That double Riemann sum is going to turn into an integral. And this is what you get here. Hold on. Let me see if I can move this up just a little bit. So in this definition, if a smooth parametric surface S is traced out by that vector equation, R of two parameters u and v, the area of the surface is just the double integral of the length of the cross product of the tangent vectors, dA. Because delta u, delta v, I want to say this the right way. Let me go back to so there's that double Riemann sum, and it's a double Riemann sum will turn into a double integral, and du dv would be, that would be your dA, your unit of area. And so that gets us down to then our definition. And so now you have a formula to find the surface area. And there it is. And let's try it out. Let's try out the formula. Okay, so I'll show you one example here. What if you wanted to find the surface area of a sphere of radius A? Okay, let's apply this formula. Find the surface area of a sphere of radius A. Well, what we have to do is we have to parameterize the sphere. So what are the parametric equations for the sphere? Well, the radius A is some fixed value, but we will use as our parameters theta and phi. And you've seen this kind of thing before. We did this before with the sphere, where we used theta and phi as our parameters. Now we have the parameterization of the sphere, and all we have to do is apply the formula. Well, to apply the formula, we need to find, well, first of all, we recognize that the domain for the sphere, phi goes from 0 to pi, and theta goes from 0 to 2 pi. Okay, that'll get us the entire sphere. And so now let's find the cross product of the two derivative vectors. Okay, so maybe, let me see if I can, hold on here. I want to see if I can have it, the whole thing show, but I don't want to highlight it. Let me just, I do, but I want to do it this way. Perfect, perfect. Okay, so look at the cross product of the two derivative vectors. So if you take the R sub phi, it has like if you look there on, well, hold on. Let me do one more thing here. Change the color here. So the parametric equations for the sphere are given in pink. And now we're doing the cross product of the derivative vectors. So what's the derivative vector of our vector function with respect to phi. Okay, that means we hold theta constant, and the three derivatives of the components are going to be a cosine phi cosine theta, a cosine phi sine theta, and negative a sine phi. That's what you see in the yellow highlighted part there on the second line. And then for r sub theta, if that there you're treating phi like a constant, so you differentiate with respect to theta, the parameters that you see in pink. And so that's going to get you it's going to get you negative a sine phi cosine, negative a sine phi sine theta. It's going to get you a sine phi cosine theta, and it's going to get you it's going to get you just 0, because the derivative of a cosine phi with respect to theta is 0. Okay, and then they don't show all the steps, but they find the cross product and they get that expression there. A squared sine squared phi cosine theta is the first component. A squared sine squared phi sine theta is the second component, and a squared sine phi cosine phi is the third component. Are there any questions so far before we're going to do another example, but I just wanted to show you this one. Who's feeling good so far? Give me a thumbs up, please. Okay, Narita's all right, and Arian's all right. Yeva and Sadana's all right, wonderful. And Abdullah, excellent. And thank you for your, thank you for your input. I appreciate it. Okay, Yeva's okay. She's a little tired, but she's here and she's okay. All right. So now what we have to do is we have to find the length of the cross product. And I mean, what they basically do here, I'm just looking at it like you are. They are factoring out, let's see. I'm just trying to see what they're doing here. I'm okay with the first step where they square each of the components. That's fine. Okay, and they factor out a to the fourth power times the sine squared of phi. That's what they do with each of those. I guess I can show it in the whiteboard. One moment. It's worth showing here. Okay, so this goes with example 1 from section 12.6. So they have a to the fourth times sine to the fourth power of phi cosine squared theta plus a to the fourth sine to the fourth power of phi times sine squared theta, plus then they have, see, I can't have too much space, a to the fourth times sine squared of phi cosine squared of phi, right? That's what they have. And the red pluses separate out. Okay, so this will equal then a to the fourth times the sine squared of phi okay, times, okay. The reason I'm saying a to the fourth is in common between all three terms. And then what else is in common is sine squared of phi. Now, yes, we have sine to the fourth of phi here, but what we would do, right, is then write sine squared of phi here, cosine squared of theta. And then we'd have, for this part, we'd have sine squared of phi, sine squared of theta. And then we're going to have just cosine squared of phi. Okay, so far so good. All right, so now if we look at this part here, we can factor out the sine squared of phi times cosine squared theta plus sine squared theta. And this here equals 1. But now what we have here is just sine squared times 1 plus cosine, sine squared of phi times 1 plus cosine squared of phi. That equals 1. And so you end up getting a to the fourth times the sine squared of phi. All right? And what you have to do now is you have to take the square root of that. If you, this is just a little aside here. Are there any questions on that? I mean, it's really, really quite beautiful, right? And this is one of these examples where nature is beautiful when you deal with, usually it's beautiful when you deal with beautiful things. You get beautiful results. So you get a squared times the sine of phi. So when we go back to the, when we go back to the example here, this should then, the length of that cross product equals a squared times the sine of phi. And that's now what you're going to put in to the formula. And, you know, they don't, well, they put it in, and then they separate out the integral as the product of two integrals, which you can do here. They don't show the iteration step, but this is true, what they're showing, and you get 4 pi a squared. So how many maybe learned a number of years ago that the surface area of a sphere with radius r is equal to 4 pi times r squared? I'm going to Google that right now. I'm going to type surface area of a sphere. If you Google it, how many are noticing 4 pi times r squared? Well, our radius was a, so 4 pi times a squared. Google it, and you'll see. Give me a thumbs up if you're seeing that. Or maybe recognize this formula from a number of years ago. All right, Norina recognizes it, and Yevas recognizes it. And so we've proven that formula now using multivariable calculus. You know, we can prove wonderful things. Now, I'll mention too something else. We're going to get to an example, but well, we see one example here. Sometimes so this here, um, which is the definition 4. This formula always works for any surface area, and it's the one I like to use. But sometimes the formula can be simplified if you have the case where you have a function you have a function of two variables. If the surface can be written as a function of two variables, this formula can actually be simplified. So how would this work? Well, they talk about what's called the surface area of a graph. So the special case of a surface where z equals f of xy lies in D, and as you know, partial derivatives, all that good stuff. The parametric equations are x equals x, y equals y, and z equals a function of x, y. Because remember, the surface is described by z equals a function of x and y. So x and y are parameters, and they equal their components. Well, you can actually compute the derivative vectors here. Okay, based on those components, r sub x is equal to I plus the partial derivative of f with respect to x times vector k. That's because when you differentiate r with respect to x, you hold the y constant, so the second component drops out. And then r sub y, well, you're holding x constant, so the first component drops out. You know, again, we are when we look at these highlighted formulas, we're looking at those parametric equations in pink there. And so the r sub y, we hold the x constant, so the first component drops out when you take the derivative. Those are now your two derivative vectors. And when you, let me just see here, let me just maybe put those in pink. Hold on. Maybe yellow this time. Here now is the cross product of those two derivative vectors. And based on that cross product, then hold on. Based on that cross product, there's the surface area formula. So you can see, let me see if I can highlight it. Yeah, there's the surface area formula. So the partial of z with respect to x is, so if you, like for the, let's just see here. Let me just go to the whiteboard to show you something on this. One moment. I think we can do it with 5-point font. So I'm writing down surface area of a graph. I'm writing down the cross product vector. Okay. And if we put the length, we know how to take the length of a vector. This component is 1 on the k. We get this. And so that's just going to give us this, right? But because z is equal to a function of x and y, we can write this square root. We can replace f with z. Trying to write it the best I can. Let me try to be a little neater. I'll get out. I'm going to get it, class, and it's going to be neat. Okay? So give me a thumbs up if you're okay with this, what you're seeing here. Give me a thumbs up if you're this part. Okay, good. So all they're doing, thank you everyone, all they're doing is because z is a function of x and y, all they're doing here is they're replacing the variable f, the function f, with function z, because z is a function of x and y. And so then this brings us back to this formula. And given that, let's look at an example. Let's look at an example, okay? Okay, let me bring it up here. Okay, so this example is an additional example to what the book has. The book has a nice example, example 2. But I want to do this example with you because you could see it in your homework or elsewhere, right? So, all right, let me give you a moment to copy this example down. So this is an interesting problem. We want to find the surface area of the part of this paraboloid, x equals y squared plus z squared, that lies inside the cylinder y squared plus z squared equals 9. Okay, an interesting problem. So the paraboloid, well, let me ask you, does the paraboloid, there's an axis that goes through the paraboloid. It's either the x-axis, y-axis, or z-axis. So which axis goes through that paraboloid? And actually also, which axis goes down the center of that cylinder? The x-axis, the y-axis, or the z-axis? That's right, Lexi. The x-axis goes down the center of the cylinder, and also the x-axis goes down the center of that paraboloid. The paraboloid opens outward along the positive x-axis. And it would keep going forever, but it gets stopped by the cylinder. This cylinder has radius 3. So think of a paraboloid. It protrudes from the origin and opens outward along the x-axis. And then it hits the cylinder. And so it can't go any further. You know, you have to, the surface area has to be finite. So it couldn't be the whole paraboloid because that would be infinite surface area. But the part of the paraboloid that lies in the cylinder is a finite. So what would this look like? Well, let's look at a picture here. I drew a little picture up here. So there's my parabola. It's actually paraboloid, I should say. I got to fix that. Let's make it, hold on one moment, black. Come on. It's paraboloid. There it is. And it opens out into the cylinder. Now, one thing of interest, of course, is, I would say, is, hold on. It's a little smaller. Tell you, they ought to have like a thing to click on sometimes. Yeah. What's that distance there? That blue distance. So you can see on the paraboloid, I drew a distance. That's right, Lexi. That would be radius, that would be 3 because that's the radius of the cylinder. So this distance is 3. All right, and we want to know what the area is, in shaded yellow here. What's the area of this surface? Well, first, I'm going to do it 2 ways. I'm going to first use the method that always works, and that's with the formula. That formula, the first formula you learned. That first formula is, again, that's That's definition 4. Okay. So the surface, and maybe I will also add an S here. This is my surface. The surface is the paraboloid. So we want to parameterize the paraboloid. This parameterization is fine. Use parameters. Since x equals y squared plus z squared, let y and z be your parameters. So r of y and z has those components you see. And of course, anytime you have parameters, you have a vector function with parameters, you have to have some restrictions on the parameters. The restrictions on these parameters are that y squared plus z squared is less than or equal to 9. And that's because any point on the surface, okay, would, in terms of y and z, it would fall inside this circle here, radius 3. And that circle of radius 3 is drawn right here for you. That region D is described by y squared plus z squared is less than or equal to 9. Please let me know if you have any questions. The parameter vectors, or the derivative vectors, are easy to get based off of our components. Okay, so now we're going to do the cross product of these two vectors and then find the length of that cross product. So if everybody's good, I'll go to the next page. Okay, so here is the cross product. And I worked out the cross product in detail for you. Let me give you a moment. So as you know, we set up the determinant here and, work it out. And we get that the cross product of these two derivative vectors in that order is equal to I minus 2yj minus 2zk. Now later on, when you learn about something called flux, okay, I want to say this the right way. This will come up in chapter 13. Flux measures the mass. It measures the rate of flow through a membrane, through a surface. And in that case, the order in which we do the cross product matters. But in this case, since we're going to, end up, I want to say it's the right way, since we're going to find the length of the cross product vector, it doesn't matter the order in which you do the cross product. If we did RZ cross RY, we'd get negative I plus 2yj plus 2zk. But when you find the length of that vector, it'll be the same as the length of this vector that we have. And so, all right, so the length of our vector is here, square root of 1 plus 4y squared plus 4z squared. And now we have our surface area, the double integral. We know what the integrand is, right? We know what the integrand is. And now it's just a matter of deciding whether we're going to integrate with respect to rectangular coordinates or polar coordinates. So for region D, you notice here, I write y squared plus z squared is less than or equal to 9. That's my region D, right? That's another way of just saying my region D. Okay. So maybe I will just add something here. So we can think of this then as double integral over my region y squared plus z squared less than or equal to 9 of the square root of 1 plus 4 times x squared plus y squared. Or sorry, 1 plus 4 times y squared plus z squared. dA. So, okay, what do you want to integrate with respect with? Polar coordinates, Lexi? Okay. So let me just see one thing here. Hold on. Yeah, all right. So if we're going to use polar coordinates, okay, then for polar, I agree with Lexi. For polar, we're going to have y equals r cosine theta and z equals r sine of theta. Okay, that's what we're going to have. So you're used to like x equals r cosine theta, y equals r sine theta. But our variables aren't x and y here. Our parameters aren't x and y. Our parameters are y and z. So if we're going to switch to new parameters, r and theta, which would be parameters for polar coordinates, we'd have to, we define y, y and z are this. And that means then that the y squared plus z squared would equal r, right? Because r squared is y squared plus z squared. Remember, this is just, you can see you know, here is, I want to, here is region D. It's a circle with a y as the axis. So going from the YZ coordinates to R theta coordinates and polar coordinates, you know, this all makes sense. So now we'll go to polar coordinates, and I guess I should say, for polar coordinates, based on this region D here, I'll highlight it with new ink. What's theta? What's theta? Gosh, come on, I don't want that. Don't give me that, please. Hold on. Get that crazy thing out of here. All right. Everything's going well, and then something crazy happens. You ever have that experience? Everything's going well, and then something crazy happens? Sure you had that, right? Okay, so based on that that circle there, I think we can, let me just go ahead. Based on this this circle, what's the radius? So for that domain D, any point inside domain D would have a radius that falls between what? What's the radius fall between? So we need, we need to get limits for a double integral. So we have radius and limits, and all right, radius goes from 0 to 3. That's right, Lexi. What about the angle theta? The angle theta goes between what? You're tracing out a whole circle, starting from here all the way to here. That's one revolution. Theta goes from what? What are the limits? 0 to 2 pi. Very good. So this then, this is now going to be our new integral. So this was the dA part, and the r squared was equal to y squared plus z squared, right? And now it's just a matter of working the integral out. This is clearly a substitution. You're going to let u equals 1 plus 4r squared. Please let me know if you have any questions. Now, at this point for the inner integral, based on your substitution that u equals 1 plus 4r squared, now you get this new integral with respect to u. So where's the 37 come from? Well, that would be 1 plus 4 times 3 squared, because the top r limit is 3. So the top u limit would be 1 plus 4 times 3 squared. That's 1 plus 4 times 9, that's 37. The bottom u limit is 1. How do you get 1? Well, that's just equal to 1 plus 4 times 0 squared. because the bottom limit, our limit is 0. So I'm not like verbally, I'm hopefully you're just comfortable with, you know, the conversion to the U integral. And, now you have to do your antiderivative with respect to U. And again, this is one of these double integrals that we can write as the product of two integrals. Well, no. Well, yeah, actually, we can do that. I just, get do the inner integral, and then, pull that out. Pull 37 to the 3/2 is 37 root 37. Maybe I'll show you that. Why that is. 37 to the 3/2 is 37 to the first power times 37 to the half power, right? Because you add the exponents, 1 plus 1/2 is 3/2. That's going to get you 37 times root 37. So that's how you get this part, right? Okay, so I'm giving you a little time to catch up here. Make sure that you're comfortable. Please let me know if you have any questions. Christia, how are you feeling with this? Are you comfortable? All right. Grayson, how are you feeling? Are you comfortable with this so far? All right. Well, let's keep going then. I hope I want to get a hit here. See, this is what really kind of bothers me, with I wish, it's just, you understand. Matthew, please tell me you're here. Matthew, are you okay with this? Thank you, Matthew. I appreciate it. I appreciate it. Appreciate it. Okay, let's keep going. Let's keep going. So let's finish this off. All right, so the surface area it turns out that the final answer is going to be pi over 6 times 37 root 37 minus 1. Now, incidentally, if you got pi over 6 times 1 minus 37 root 37, how do you know that's wrong? How do you know that answer is wrong? 1 minus 37 root 37 times pi over 6. Why would that answer be wrong for surface area? That's right, Norina. It's negative. Surface area is positive, always positive. Very good. All right, now there is a you remember I mentioned there's a second method. It does not work all the time. You cannot depend on the second method working all the time. But because x is a function of y and z, okay, the surface area for the graph would be given by this double integral. So you integrate, you differentiate x with respect to y and x with respect to z, because x is the dependent variable and y and z are your independent variables. So the formula in the book where they talk about a graph of the surface area formula for a graph of a function, that formula is where z is a function of x and y. But here, x is a function of y and z. So you have to alter the formula a little bit. And that's what I did here. And when you do that, you get to the, you get to the double integral more quickly, because you didn't have to worry about parameterizing. You didn't have to come up with a vector function of two parameters to describe the surface. But again, the problem with this second method is method 2 only works sometimes. In other words, formula 4 or formula 6 in the book in section 12.6, which we adapted because we have x as a function. We changed it because we have x as a function of y and z. It only works, sometimes, and that's, when you can write one function, you can write one variable as a function of the other two variables. And so, you work it out, and of course, now this integral here, this double integral is exactly the double integral that we got when we used the first method, and where we parameterized the surface. And of course, you're going to get pi over 6 times 37 root 37 minus 1, of course. Okay, are there any questions on that? How many would use the second method if they could? How many might use the second method if they could? Okay, Christopher would use it if he could. Okay, and you're certainly able to do that. Do you think on your next exam you might have a situation, and Samuel would, do you think you might need to know both methods for your exam and your homework for your next exam and your homework? Do you think you'd be able to know how to, do you think you'd need to know to do it both ways? Do you think you would need to know both methods? That's not right. Norina says, yep, that's right. Yes, absolutely. Okay, so, and again, I generally use the first method all the time where I parameterize the surface, because then that works all the time. But, all right, great. Who's feeling good before I stop this recording? We're going to take another break, but who's feeling good with this? Who's feeling comfortable? Yeva is good. Okay. I hear you, Norina, Samuel, and let me see who was Christopher. Good. All right. Good. And I'll just ask again, give folks. Christia, how do you feel? Are you comfortable with this? Grayson, are you comfortable? I'm asking both of you. All right, Mary, how about you? What do you think, Mary? Are you reasonably comfortable? Okay, wonderful. Wonderful. Okay, very good. Well, I'm going to go ahead and stop the recording here. Excellent.